the last lecture, we have shown how to relax two of the assumptions that we made regarding an ideal transformer, that is of lossless windings and no leakage. And we found that a practical transformer model can be derived from an ideal transformer, which is represented by a core and two windings, by incorporating the resistance of the windings and the effect of leakage flux can be incorporated by assuming a leakage inductance in series with both the windings R1, R2, L1, L2, V1. The load will usually be connected here. This voltage is V2. The current flowing in coil 1 is I1, flowing in coil 2 is I2. The induced voltage across coil 1 is E1, while the induced voltage across coil 2 is E2. Then we have seen V1 equal to R1 I1 plus L1 dI1 dt plus E1 and E2 equal to R2 I2 plus L2 dI2 dt plus V2. And as in the case of an ideal transformer, E1 by E2 equal to N1 by N2. However, this still does not take into account the magnetization current, that is the current to be drawn by a practical transformer even when I2 is 0. This can be easily incorporated by assuming a magnetization inductance across the coil L1. This is so because the induced voltage E1 leads the flux by 90 degree. So, a inductance connected across E1, the current flowing through the inductance connected across E1 will lag E1 by 90 degree and will be in phase with the core flux phi m, which is responsible for generating the core flux phi m. So, the effect of finite permeability of a practical single phase transformer is taken care of by considering a magnetizing inductance across the winding and leakage inductance in series with the winding. The last detail that needs to be incorporated in the model of a single phase transformer are the core losses. It is well known that when a ferromagnetic material is subjected to an alternating flux, then two types of losses occur. One is the hysteresis loss, another is the eddy current loss. Both of them are increases with increase in the flux density and the frequency of the alternating current waveform. Although these relations are not always linear, for the hysteresis loss, the loss is proportional, power loss is proportional to the frequency, however, not for the eddy current loss. But in a normal application of a transformer, normally the supply frequency and the voltage will be constant. Therefore, for a given application, there will not be variation with frequency, since the frequency is constant. These losses can be approximated by losses occurring in some resistances, fictitious resistances that are connected across the coil. Therefore, in order to represent the losses that occur in a practical transformer, some core loss resistance is connected across the coil, that is parallel to the magnetization branch. Therefore, the complete model of a practical transformer incorporating a ideal transformer looks as follows. First, let us put the winding resistance of coil 1, then the leakage inductance of coil 1, and then the coil 1 of the ideal transformer, in order to take care of the finite magnetization current, we connect a magnetization inductance, and to take care of the core loss, we connect a core loss resistance. This is the ideal transformer. The secondary side, similarly, there will be a leakage inductance L2 and the winding resistance R2. The applied voltage on the primary side is V1, current through the primary is I1, the magnetizing current is the IM, the core loss component of the current is IC, together they are called the no load current I0. The current flowing through the ideal transformer is the reflection of the load current I2 dash, and the current in the load circuit is I2, the load voltage being V2. This is the complete model of a practical single phase transformer, taking into account the non-idealities, which also incorporates a ideal transformer. In phasor form, the equations can be written as V1 equal to R1 I1 plus J XL1 I1 plus E1 and E2 equal to R2 I2 plus J XL2 I2 plus V2, V2 equal to ZL I2, I1 equal to I2 dash plus IM plus IC equal to I2 dash plus I0. IM equal to E1 by JXM, IC equal to E1 by R0, E2 equal to N2 by N1 E1, and I2 dash equal to N2 by N1 I2. This set of equation is the defines the complete steady state model of a practical single phase transformer. Normally, the steady state phasor relationships are described by a phasor diagram. Hence, it will be interesting to draw the phasor diagram of a single phase transformer, which is shown next. Again, we draw the phasor diagram taking the core flux phi m to be the reference phasor. Both E1 and E2 will lead phi m by 90 degree. Then the current I2 is given by which will lag, assume to lag E2 by an angle phi. The phasor I2 dash will be in phase with I2 and will be in fact a scaled version of I2. The current I1 can be obtained by phasor sum of I2 dashed with Im, which is in phase with phi m, and IC, which is in phase with E1, which gives me the phasor I1. The voltage V1 can be obtained from the first equation, E1 plus I1 R1 plus J XL 1 I1, this is I1 R1. So, this is the phasor V1. Similarly, phasor V2 can be obtained by, from the second equation, it is E2 minus I2 R2 minus J XL2 I2 which can be used for solving any problem related to single phase transformer. However, if we take a closer look at the circuit model of the single phase transformer that we have so derived, we will find that this is not very suitable for applying the known circuit analysis techniques, since there is a ideal transformer between the two parts. Hence, we cannot apply, for example, a KCL or KVL where the loop current is expected to flow across the ideal transformer. This path, we cannot write a loop equation involving a path like this, since we do not know the voltage drop across the ideal transformer. Therefore, it will be more convenient if we can eliminate this ideal transformer. This is done by referring the secondary of the ideal transformer to the primary, or vice versa, the primary can also be referred to the secondary. Let us see the first option. By referring, we means we connect an equivalent circuit across the terminals of the ideal transformer, so that the current drawn by the equivalent circuit is the same I2 dust as it is drawn by the ideal transformer. Let us see what should be that circuit. The current I2 is given by E2 divided by ZL plus R2 plus J XL2. And I2 dash equal to N2 I2 by N1. Therefore, I2 dash equal to N2 by N1 E2 divided by ZL plus R2 plus JXL2, or I can write I2 dash to be N2 by N1 square into N1 by N2 E2 divided by ZL plus R2 plus JXL2. But N1 by N2 E2 is equal to E1. Therefore, I2 dash equal to E1 divided by N1 by N2 square into ZL plus R2 plus JXL2. Now, let us have a look at the model that we have, circuit model that we have obtained. The voltage across these two terminals is E1 and the current drawn from these terminals is I2 dash. Now, the same current I2 dash will flow provided an impedance of this form is connected across these terminals. Therefore, we can replace the ideal transformer and the secondary circuit after that by an equivalent impedance given by this formula. Hence, the original circuit model I1, I0, IM, IC, I2 dash, I2 and V2. This was the original circuit model of the practical single phase transformer, which incorporated an ideal transformer with primary turns N1 and secondary turns N2. This circuit model we argue can be replaced by an equivalent circuit model, where up to this point there is no change, but the rest of the circuit is replaced by an equivalent circuit where the elements are given by so that the current drawn on this branch is I2 dash as in the case of the original model. The required equivalent impedances are related to the actual impedances as follows: R2 dash equal to N1 by N2 whole square R2, XL2 dash equal to N1 by N2 square XL2, and ZL2 dash equal to N1 by N2 square ZL2. The dashed quantities are called the referred impedance of the secondary side referred to the primary side, and the equivalent circuit thus obtained is called the exact equivalent circuit of a single phase transformer referred to the primary side, that is the side with suffix 1 and number of turns N1. Now, let us see the actual secondary current was I2. The power loss in the resistance was I2 square R2. This was the actual power loss in the secondary circuit. In the equivalent circuit, the power loss is I2 dash square R2 dash, but I2 dash itself is equal to N2 by N1 I2, and R2 dash equal to N1 by N2 square R2. Therefore, I2 dash square R2 dash is same as I2 square R2. Therefore, we see that the power consumed by the secondary resistance is not changed by referring this circuit. So, it preserves the power relations. What will be the referred secondary voltage V2 dash? We call this V2 dash, then V2 dash equal to I2 dash ZL2 dash, but I2 dash equal to N2 by N1 I1, I2, and ZL2 dash equal to N1 by N2 whole square ZL2. Therefore, V2 dash equal to I2 dash ZL2 dash is equal to N2 by N1 I2 into into N1 by N2 whole square Z L2 equal to N1 by N2 into V2. So, we have I2 dash equal to N2 by N1 into I2 and V2 dash equal to N1 by N2 into V2. Therefore, V2 dash I2 dash equal to V2 I2. So, the kVA consumed by the referred load circuit is same as the kVA consumed by the original load circuit. So, we have seen that the load circuit can be referred to the source side by multiplying the load side parameter values, that is the impedances, by the turns ratio square. Similar thing can be done for the source side, that is, instead of referring the rest of the circuit across this terminal, it is possible to refer the left of the circuit across this terminal, in which case the secondary side impedances, voltages and currents will remain same, while the impedances of the primary side will change. Let us see what will be the relations. The actual circuit model which is given by this diagram, we now want to replace it by an equivalent circuit with an equivalent network connected across these two terminals. This circuit which is also an equivalent circuit referred to the primary side was obtained by replacing the right hand side of the circuit after this point by an equivalent impedance, and this circuit was called the exact equivalent circuit of the transformer referred to the primary side, since the impedance on the secondary sides were referred by the turns ratio. Now, we want to derive an equivalent circuit of the transformer referred to the secondary side, where the secondary impedances will remain as it is, however, the primary source and impedance will be referred to the secondary side. Although it is possible to connect different types of impedances, we would like to retain the structure of the or the topology of the circuit on the primary side as far as possible. Therefore, we assume the equivalent circuit to be as follows. The secondary side does not change, me. We would like to retain the structure of the primary circuit. Therefore, we will have an equivalent impedance in series, equivalent inductance in series, and call it J X L 1 dash. A shunt branch consisting of a shunt reactor J X M dash and R 0 dash and a series resistance R 1 dash connected to a source V 1 dash. Our objective is to find out an expression of the dashed quantity, so that when the dashed quantities are applied to the circuit, the secondary current remains I 2 and the secondary voltage becomes V 2 when the load connected is Z L 2. Let this current be I 1 dash. The voltage E 2 equal to I 2 into also E 2 equal to therefore, multiplying both sides by N 1 by N 2, can write this or can be written as but n2 I2 divided by n1 equal to I2 dash. And n1 by n2 square into these impedances are however, from our previous discussion we have seen that this quantity I2 dash into ZL2 dash into R2 dash plus JXL2 dash, this is equal to E1 and is given by V1 minus I1 R1 plus JXL1. Therefore, V1 minus I1 R1 plus JXL1 equal to V1 dash minus I1 dash R1 plus JXL1 into N1 by N2. Equating terms, we can say V1 equal to N1 by N2 into V1 dash or V1 dash equal to N2 by N1 into V1. Similarly, I1 R1 plus JXL1 equal to N1 by N2 I1 dash into R1 plus dash JXL1 dash. If we want the power relations, power consumed by the resistance R1 should be same as the power consumed by the resistance R1 dashed in the equivalent circuit, then we must have I1 square R1 equal to I1 dash square R1 dash. This will be ensured if I define I1 dash equal to N2 by N1 into I1 and R1 dash equal to N1 by N2 square sorry, n2 by n1 square into R1. I1 dash equal to n1 by n2 square into I1 and I2 dash square R1 dash square equal to n2 by n1 square into R1. Therefore, we will say R1 dashed will be equal to n2 by n1 square into R1. Similarly, x L1 dash equal to n2 by n1 square into x L1, and we have already obtained V1 dash equal to n2 by n1 into V1. Regarding the shunt branches, again if we want the impedances, I mean the power balance to be maintained, then I should have E2 square by R0 dashed should be equal to E1 square by R0, or R0 dashed should be equal to E2 by E1 whole square into R0. But E2 by E1 equal to N2 by N1. Therefore, R0 dashed is equal to N2 by N1 square R0. Similarly, Xm dashed equal to N2 by N1 whole square Xm. Therefore, the equivalent circuit of the single phase transformer referred to the secondary or the load side will be similar to the previous circuit, except the parameter values will now be different. It is given by a similar circuit relationships are V1 dash equal to N2 by N1 into V1, I1 dashed equal to N1 by N2 into I1, I0 dash equal to N1 by N2 into I0, IC dashed equal to N1 by N2 into IC, Im dash equal to N1 by N2 into Im. The parameters are R1 dash equal to N2 by N1 square into R1, x L1 dash equal to N2 by N1 in square into x L1, x m dash equal to N2 by N1 square x m, and R0 dashed equal to N2 by N1 square into R0. So, this is the equivalent circuit of a practical single phase transformer referred to the secondary or the load side. While this was the equivalent circuit of the same single phase transformer referred to the primary or the source side. They are identical as far as the circuit structure are concerned. They are identical except that the parameter values of the two circuits are different.